Good evening, good morning, everybody, and welcome to this fourth of 6 webinars from IMI. Today we're going to be covering control loops. I will give it 30 seconds or so just to get a few more people in the room. But for those that haven't been, this is the first one. My name is Rob Green. I am the Hydronic College trainer based out of the UK. So, and as part of my role, I'm looking after the ANZ market from a training and technical perspective. And this is now the fourth of 6 webinars. So we've covered manual balancing, dynamic balancing, and we're going to start looking into the world of control today. So I shall share my screen. And in a moment, I'm going to just leave the welcome page up. I'm just going to launch a quick poll. So we've got a couple of polls to launch now, just to gauge some interest from the room, really. So this first poll I'm going to launch up is regarding to preferred channels for finding out about trainings in HVAC, so we can make sure we're targeting the right places. So you should see in the middle of your screen a little pop-up with a poll. If I could ask you to answer it for me, and we'll get some feedback. So thank you very much. Okay, I can see we've got a few coming in. We've had about 7 people respond. Fantastic. Thank you very much. So let's just quickly, I'm going to launch another poll, so I'm going to ask a little bit more from you. But before we do, I just want to do a little bit of housekeeping for today's webinar series. We will be recording the webinar. In fact, I will double check it is recording. Yes, it is recording. Fantastic. We'll be recording the webinar today. During the process of the webinar, your mic and camera is going to be disabled. And we're going to have, at the end, we'll have a bit of time for a Q&A session. But there is a anonymous Q&A functionality built into this webinar. At the top of your screen, you should see there is a little Q&A section. You can see a little Q&A button sort of here. If you ask your questions, and we'll come at the end of the webinar, we'll collect the questions together, and any questions you've got, we'll answer at the end. And also what I tend to do is open up the mics and cameras at the end. So if you wanted to ask your question in person, we can do that. And also we will be, alongside the recording, releasing the slide packs for this webinar as well. So that's another thing that I know a lot of people are after. So we're going to make sure that's going to be available to you at the end of, or well, later this week, once we've collated all of the information. And before we start, I do just have a further ask. Regarding to training, we're wanting to make sure we are training on the right topics for the region. So we've got a little question, bit of a free question on what further topics you would like to see us to train, because we're coming towards the end of this session, these 4 of 6. So we're going to look at the next series going forward, and we'd like to know if there's anything in particular that's coming out in the region. Okay, fantastic. That poll's working away. So let's make a start on the material. So agenda to cover today in the next sort of 40 minutes, 45 minutes or so. We're going to do a recap, very quick recap on the last 3 sessions. We're then going to delve into some new material. And the purpose of today's webinar is to get an introduction to different kinds of two-way control circuits. And in particular, we're going to be looking at 2 types of circuit. We're going to be looking at a two-way direct circuit and a two-way injection circuit. And we're going to look at the different application ideas, different considerations one must take when we are looking at designing, specifying, installing these type of circuits. And then in the webinar in I think it's 2 weeks time, we're going to carry on a little bit more on that vein and look at some more applications on selection of products and different reasons for selecting different types of products. But we wanted to start off with looking at actually what these circuits are. So to begin, I want to do a bit of a quick recap around what we covered in the first 4 sessions here. And the main thing we were looking at is balancing. And what is the purpose of balancing? And it's really, really important, even when we're talking about this control side of things, that we ensure the balancing has been done in the correct manner and in the most efficient way. So we need to make sure we are adjusting design flows into all terminal units to my design conditions, i.e. with my control valves fully open, my full load condition of the system. And the really key thing we covered is ensuring we were doing that with minimum additional pressure drops in the system. Making sure it was a highly efficient balance. A system is not balanced until we have optimized that system. And if you're interested in finding out how you can do that, different methods of ways of doing it, we've got the previous webinars published as well. So if you didn't get a chance to jump onto those earlier on, you can find on our links on our website to get access to those recordings as well. And then we introduced something new in the 3rd session, which was now I think 6 weeks ago or so, just before the new year, and it was talking about differential pressure variations in systems. And this is something that's really important when we're coming to control, because actually, if we take a look at this graphic here, this is a fairly typical graphic showing how much flow we need in a system or a device based on its emission. Now, in many markets, we're running, and in particular, if you take somewhere like Melbourne, we design a cooling system. We're not running that peak temperature now. I know down in Australia and New Zealand, you're coming into your summer period. In fact, no, you're well into the summer period now, should I say? So you're at these peak cooling demands. But outside of that, you still need to cool that building, but not to the same amount. And actually, you can look at like 80% of the time in some examples. It's usually in the sort of southern hemisphere, round about 60 to 70% of the time, you're below 50% of your design load. So you've designed a system to, I don't know, 5 megawatts. So it's a huge system at 5 megawatts. But actually, for 50% of that year, you're only at, 60, 70% of that season, you're only at a half of that load. And half of that load is only going to equate to 20% of the flow. And where this becomes really interesting for a hydronic engineer is when we look at my relation between flow and differential pressure, where my relation between differential pressure and flow is this famous inverse square law, where we look at it and we say the differential pressure through a pipe, a system, a device, any static part of a system is proportional to the square of the flow going through it. So when we're now running at 50% load, 20% flow, actually, we're only running at around 4% of the pressure drop in that system. So my pump is sized, my pump is operating at that full load, that full, let's say this 5 megawatt system. It could well be, I don't know, 3.5 bar pump head that it needs to satisfy everything on that warmest day of the year. And for around 60, 70% of the year, only 4% of those pressure drops are in the system. And that pressure has to go somewhere. There needs to be devices to take out that differential pressure. And in reality, the dynamic devices we have in systems are control valves. And what happens is that pump head is applying itself almost entirely on those control valves. And in the session we will learn in 2 weeks' time or so, we'll look at how that affects a control valve. But it's something to bear in mind from a dynamic. We looked at dynamic balancing in the last session, and this is something really important as to why dynamic balancing is there. It's because of these huge variations in differential pressure during the operational time of a system. And if we look at a system in general, often it gets touted, well, yes, we have a variable speed pump, so it's going to deal with these changes. But if my pump is sized to achieve a given design head and it is operating at that design head in all times, which is fairly common on your sensor location, the variations are not going to be uniform throughout that system. So in order to satisfy this device here, for example, we may still need 100 kilopascals in my pump, but that's going to be masses of excess of differential pressure throughout the control valves. So we need to think about ways we can do that. And we were looking at that in the last session with dynamic balancing valves, looking at devices that, such as differential pressure control valves and pressure independent control valves, that are able to deal with these changes and automatically adjust to these changes in differential pressure. Because the pump itself is not going to be able to do it. And that's just that recap around that. And we were looking at ways and means or devices we can do that. And we're going to see in 2 sessions time, not 2 sessions time, in 2 weeks time, how we can deal with that and how we can make sure we are correctly specifying and sizing our control devices. But what I want to do today is actually look at some of these control loops in action. And the 2 we're going to be covering today are 2-way direct circuits. So circuits like this, very, very typical for things like fan coil units, chilled beams, all of this sort of things, and something called an injection circuit, which is something like this, where we have a secondary pump providing a constant flow through this secondary side of the system. And this is something that's very typical around things like air handling units, where we need a higher level of control than something like a fan coil. And I'll talk about why we introduced the injection circuit. Very, very prevalent in Europe. Being a proud English guy, something they don't really do in the UK. When I go over to Europe, they say, well, they don't. But there's some real good reasons for it, and we can really get improvements in control with there. So we're going to talk about why and how we do that in these next sort of 30 minutes or so. And we're going to just touch on this. As I've said during these webinar processes, these are sort of 45-minute to an hour webinar sessions covering material that we would generally cover when we train our internal staff in a week. So we're just kind of distilling it to give a bit of a taste of some of the things you may need to consider when you're looking at these circuits. And we want to analyze them, and we're going to have some fundamental rules when we're looking at analysis. And for me, the number one rule is always going to be asking what our customer wants to achieve. There is no sense in making something that is able to control absolutely finitely my air temperature in a system where they're saying, oh, it's just the open hall of a mall. If the temperature varies up and down a few degrees, it's not going to be too bad. And conversely, we don't want to do something really cheap, cheerful, and easy in a data center or a hospital environment where it's really key. We really tightly control those temperatures. One of the most, I would say, difficult parts is we want to locate what we call the active differential pressure sources in that circuit. So where is the pressure differential coming from in those circuits? We then want to estimate the differential pressure at the different parts. Locate any dynamic devices, i.e. components that can take different positions, control valves, DPCVs, PICVs. And for a control valve, we want to consider 2 extreme cases. When the valve is fully open, i.e. at design conditions, the differential pressure is the lowest, and when the valve is fully shut, in my low load condition, my practically zero load, when the differential pressure at that valve is the highest. And we need to make sure we take account of both of those so we can have a play off and make sure we get the most efficient solution. Also, we need to find if and where the variable flow is and if and where the constant flow is in a system. And determining if and how the design flows can be set. So number 7 is talking about the balancing. What procedure do we use to balance these circuits? And we're going to learn about something called authority in 2 weeks' time, but we need to determine the minimum authority for the control valves, which is really important with 2-way control valves. Often I see designs where they're only considering the design authority, i.e. the best possible case, But minimal authority is where we're talking about this 60–70% of the year, where we only have 4% of the pressure drops in the system. My control valves are seeing the highest differential pressure. They're going to be spending most of their life in that scenario. So we need to ensure we're designing to achieve that. We also need to check flow compatibility can be ensured if it's needed. At every interface, we have sufficient flow to satisfy the secondary circuit. And at mixing points, so if we have a point in the circuit where we're mixing, we need to take into account conservation of flow, that the flow from the primary side plus the flow from the bypass is equal to the secondary flow. Seems pretty simple, but if we don't take that into account, we're going to be in a world of pain when we try and set that system up. And really importantly, energy conservation, ensuring that the flows between the primary and the bypass are correct based on their temperatures to achieve the flow we need on the secondary side of the circuit at the temperature we need to achieve it at. And this will make a little bit more sense when we talk about injection circuits later on in this webinar, and compatibility between my differential temperatures on the primary and secondary side. Because again, we can't get into how do we do this. We need to make sure this is right. We can't magic our way around this. We need to make sure the fundamental design conditions are correct. So these are my 10 fundamental rules. And the first I'm going to look at is a two-way direct circuit. So this is flow control for all kinds of units or circuits. Here, the supply temperature from the distribution here is transferred. So on the distribution side, we are flowing that same temperature into my terminal unit or into my circuit. And we are varying the flow and the velocity through this via opening and closing of this valve. So my temperatures do not change, but my flow does. So let's have a look at it, and let's have a look at asking some of our fundamental questions. So here we have a very simple setup with a control valve serving an emitter. This could be a fan coil unit, for example. And we want to ask some of our questions. On the primary side, is it an active circuit or a passive circuit? Is there an available differential pressure driving the flow through that circuit? My primary and secondary flows, are they variable? Are they constant? What is the flow direction in the circuit? What are my temperatures? My primary temperature, my secondary temperature. So my primary from the system, my secondary serving the device, and my return temperature coming back into the system. What control mode do we need? Does it want to be on off? Fully proportional? 3-point raise lower? My minimum and my design authority? And very importantly, where's my balancing function? What's the location of that valve? What procedure am I going to use to balance this circuit? And this one in particular is very important when we're talking about control, because we need to ensure we're satisfying and setting design conditions. So these are the sort of questions we're going to ask ourselves when we're looking at designing a circuit. And let's have a look at 3 different two-way direct circuits. We have our simplified option with a two-way control valve and a balancing valve. We could also look at something like a combined balancing and control valve. So this valve both does the function of balancing and control. And finally, we can look at a differential pressure control type valve, a pressure independent control valve. So this valve also has a differential pressure controller to stabilize the differential pressure across that valve, as we learnt about last week. And we can talk about why that's doing it. And the main reason is actually for preserving valve authority for control. So in the case of my direct circuit, we have an active primary network. We have an available pressure driving flow through this network. Therefore, we're classifying as active. In the case of the flows, we have variable primary and secondary flow. Because my flow on the primary side is going to vary depending on my demand on each of these circuits, it's exactly the same idea. The flow is going to vary on the primary side. And because it's got nowhere to go, it's also varying on the secondary side. In terms of my temperatures, my secondary temperature into my device is equal to my primary temperature. There's no mixing point in this circuit. It's very simple. For proportional control, on a non-pressure independent device, we have my minimum authority, which is going to be equal to the differential pressure across the control valve at design conditions, divided by the pump head. Because we're going to say at minimum conditions, when everything is pretty much closed, there's no differential pressure in the primary network. So therefore, the pressure being produced by the pump is going to be seen by every single control valve in that circuit. And then my design authority, which is going to be equal to the differential pressure across the valve at design conditions, divided by the available head at that valve. So let's look at a sizing example for two-way direct circuits. And in this example, we are looking at, this is a heating example, a design power of 20 kilowatts with a supply temperature of 70 degrees C and a return temperature of 50 degrees C. A pump head of 100 kilopascals, an available differential pressure of 50, so i.e. at design conditions, 50 kilopascals has been lost in the primary network before it got to this particular device, and a coil pressure drop of 10 kilopascals. So you'll notice we don't have a flow here, but we can calculate it. So if we calculate the flow at an average temperature in the coil of 60 degrees C, we have a density of 983.2 kilograms per meter cubed and a specific heat capacity of just under 4.2 kilojoules per kilogram Kelvin. So from that, I can calculate a design flow. And this is my calculator from design flow. It is my design power divided by my differential temperature multiplied by my density multiplied by specific heat, with a couple of correction factors in there for good luck as well. And this calculates out at a design flow of 875 litres an hour. For example, we could do that a little bit less accurately and calculate for water at 20 degrees C, where the calculation would come out at 860 litres per hour. So slight difference, but we want to be accurate. So let's make sure we get as accurate as possible on there. So let's have a look. How would we size the? We're going to look at both of these circuits together. How would we size the control valve for each of these circuits? And we're going to start off by sizing it for the required differential pressure, and it needs to be the largest between 0.25 times the pump head, and the reason for that is my design authority, my minimum authority, if you remember, was the control valve pressure drop divided by my pump head. So therefore, if the control valve pressure drop is 25% of that, we have a minimum authority of 0.25. And we'll see why we care about that in a couple of weeks' time. So in the case of a standard control valve, that's going to be, it's going to be the same. And the differential pressure at design conditions. So the maximum the control valve can have is going to be my available pressure, 50, minus 10 for my coil, minus a minimum of 3 for a balancing valve, i.e. 37 kilopascals. Slightly easier with the combined valve, we only take off the coil pressure drop. And the reason we want to size it for the largest is we're not adding any additional pump head to that. We have an available of 50. So let's make sure we make it as efficient as possible. And actually, sounds a bit backwards. The higher pressure drop in the control valve is, the better control you're going to get. And we want to optimize it. So we don't want to exceed that minimum available head. If we can't fulfill 25 kilopascals because, for example, the available head was too low, we want to start looking at standalone differential pressure control or pressure independent control valves, because if we can't achieve 25 kilopascals, we're not going to get the minimum authority we need for a good level of control. So let's have a look at sizing a valve here for 875 litres an hour. For 875 litres an hour, what we want to do is, first of all, work out what is, at 37 kilopascals, being the larger of the two figures, what would the KV, what would the capacity for flow be for a valve if we could choose the exact valve we needed to get 37 kilopascals at design flow? And that comes out with a KV of 1.44. And what we tend to do is we then choose the next biggest valve that can achieve that in general. And that is going to be a DN15 control valve with a KVS of 1.6, which is going to give me a differential pressure across the valve of 30 kilopascals, i.e. still more than 25. So we know the minimum authority is still going to be good. At that point, we can then size my balancing valve to take out the difference between the available head and the other parts in that circuit. So pretty simple bit of mathematics. We take the available differential pressure, take off the coil pressure drop, and finally take off the valve. So we size our balancing valve to 10 kilopascals at my design flow of 875. And at that point, that's, in this example, a STAD 20 with a setting of 2.52. Seems like quite a few steps. Actually, in webinar 6, we're going to be looking at the use of our software, HiSelect, where we can take all of these steps out, and by just inputting a few different bits, it's going to calculate all of this for us. So a little bit of an advertisement for the final webinar in this series here as well. For the balancing control valve, it's in essence very simple. We have an adjustable KV value on that valve. So we just need to find out what the KV is for a differential pressure of 40 kilopascals, and then choose the appropriate valve. In this case, a DN20 valve at a setting of 7.6. You may say to me, hang on, Rob, you're missing one here. What about a pressure independent control valve? And as we learned last session, pressure independent control valves are actually extremely easy to size. We just need to know the flow rate. The differential pressure controller within it is going to compensate for any changes in differential pressure, ensuring a high level of authority. So in this case, for a flow of 875 litres an hour, that would be one of our DN20 TA modulators set at 8.3 turns. So that's my valve selection criteria. We've now selected the valves there for these two-way direct circuits. Let's have a look at how the authority works out. Let's calculate the authority on these. We're going to start out with a standard one. So we have my minimum is, apologies, the figures are different between this page and this page. 27 divided by 100, which is 0.27. And my design is my pressure drop on my valve divided by my available head at design conditions, because we're talking design, 0.54. We'll talk about authority next week, or sorry, 2 weeks' time. But minimum should always be above 0.25, and a good gauge for design is around 0.5. On the TVVCM valve, it's a slightly different design. So at my design flow rate, we would have 19 kilopascals across the control section of it. So that would give me an authority of 0.19. versus at design an authority of 0.38. So we can see in this particular example, the standard control valve and balancing valve is going to win out. It's going to give me a better authority if we're talking standard control. And again, really, really easy with the pressure independent control valve. We need to make sure my authority, or sorry, it guarantees a minimum authority of greater than 0.7. And we'll talk about that, why it's not 1. Some people like to talk about pressure independent control valves having an authority of 1. It is simply not possible. Physics dictates you can't do it, but a good control valve, good pressure independent control valve is going to be a minimum authority of 0.7. So again, you can really see here why pressure independent control valves start to become the default de facto choice for a high level of control. So the question is going to be, how do we increase my authority? We could decrease the available differential pressure. I make less differential pressure available. But that's going to mean bigger pipes in my circuit, lower pressure drops in my circuit, readjusting my balancing valve. Not really a good solution. Another option, we could change the top of that circuit, make that bigger. We could decrease the size of the control valve, i.e. restrict that control valve down further, increase the authority. But again, downside is we might have less flow than expected, or we have to increase the available head, so we're not efficiently doing the system. The option you could look at, and actually part of our business would do, not the climate control side of our business, the process automation side, we could choose a special valve with a special KVS that has got exactly what we need, but that's going to come with a pretty significant cost. So again, not ideal from HVAC, where we're talking valves in the hundreds, high hundreds. Or we could use a differential pressure controller, stabilize the differential pressure on the branch. That's going to reduce the variation in head here. Or use pressure independent control valves, or use something like our TA Smart, a valve that is going to react to changes in flow and maintain a stable flow. So that is a little bit around what we need to do. And I'm going to introduce now very briefly a subject we're going to cover in a lot more detail in the next webinar. But that is about in a two-way direct circuit, and this can also apply to an injection circuit, why we need to have a certain set of conditions and what we want to do. And there's something called an equal percentage characteristic control valve that is extremely important for room temperature control, because my target is to have a linear characteristic between my input to my circuit, i.e. my control input, and my output, i.e. how much heating or cooling power I'm delivering to my room, to my process, whatever it may be. And we have a number of things that make up this. We have my terminal characteristic. Again, this is a thermal characteristic of a coil. We can't really change that. When we've selected a coil, that's what it is. So what we end up doing is we take a valve that matches and opposes this characteristic, because when we put the two together, we get then a nice straight line. We have my actuator characteristic, very simple, input versus lift. We want that to be linear to make it nice and simple, to retain a high level of control across that actuator. And then finally, we have another thing, which is what we call in my hydronic circuit variation, i.e. my valve authority. And when we put all four of these things together, my target is going to be this linear control. I often put this akin to, say, the accelerator pedal control on your car. If you start going up a hill, you want to just put a little bit more power on and to maintain a steady speed. If this was top end, you got loads, and then bottom end, you got nothing, you'd really struggle to maintain a fixed speed in your car. But we'll cover that in a lot more detail in the session in a couple of weeks' time. So that was the two-way direct circuit, a fairly simple setup. The next one I want to talk about is a two-way injection circuit. This is for controlling the supply temperature into a secondary side. So it's an injection mixing circuit. Here we are mixing an amount of my return water into my supply to vary and control that supply temperature. That leads to a much higher level of control, because we end up having a constant flow on the secondary side. So my flow, my velocity in my coil is constant. So my heat transfer is a lot more constant in there. So we get a lot higher level of control, particularly at lower loads. So that's one of the main reasons these are used for things like air handling units, where we want to have a higher level of control than something like a fan coil. With the downside of you do need to provide a secondary pump. So we're going to ask my same questions again: active or passive primary, variable or constant flows, what's my flow direction, what are my temperatures, what control mode, so on and so forth. But let's have a look at it in some detail. So in this case, we have active primary and secondary networks. We have an active pressure source here from the primary pumps and an active pressure source on the secondary side from the secondary side pump. In this example, we're going to be talking about a variable primary flow because when we change this valve position, we're varying the primary flow. But we're using these on a constant secondary flow. So the flow on the secondary side is always going to be the same, and we're varying the load via varying my supply temperature. In the case of heating, my secondary temperature is going to be lower than my primary temperature because we are mixing down the temperature. In the case of cooling, it's the inverse. My secondary temperature is going to be higher than my primary temperature because we're injecting hotter water into the flow to mix up that temperature on the secondary side, sorry. And the secondary temperature can only be equal to the primary temperature at design conditions. So i.e. when we have matched flow primary and secondary side, we would have no flow in the bypass. So my primary temperature would be the same as my secondary temperature at design conditions. For proportional control authority, we have these same relations as we saw before. And in this case, the primary circuit is not influenced by the terminal unit pressure drop because we have my secondary side pump that is dealing with the pressure drop on the secondary side. So let's have a look at some characteristics and why these are often better. And if we look at my flow versus power relationship for direct circuits and two-way injection circuits, you'll see this is a much flatter circuit in this lighter blue color here. So my changes in flow give a lower change in power. So I can provide better control over these examples. It's the better solution if we're wanting high level of control, in particular at low loads. Because in particular at low flows, when my velocity starts to drop off, this red example is an ideal solution. Chances are actually below 20% flow, depending on the coil size, we're going to get a massive cliff edge drop off in output. So actually, we're going to get very little control of that bottom end. Whereas we're going to maintain a stable level of control with my injection type circuit. Apologies, this one snuck in. So let's have a look at a sizing example now for a circuit. And we've got a circuit here where we've been told the design flow. This is a cooling circuit, and the design flow to this circuit is 72 meters cubed per hour. So a pretty substantial circuit. My supply and return temperature at design conditions is 15 degrees supply, 18 degrees return. So therefore my return back into my primary system is also going to be 18 degrees. There's nowhere for the water to go. It has to go back at 18. We're supplying this circuit with a 6-degree flow temperature. My primary pump head is 60 kilopascals. My available head is 45. And my circuit pressure drop here on the secondary side is 65 kilopascals. So here, first thing we need to do is energy conservation. and flow conservation. We need to ensure that the primary flow multiplied by the primary differential temperature, i.e. how much power we're delivering on the primary side, is equal to the power being consumed on the secondary side. We have to have an energy balance. Physically, you can't. You do not make or destroy energy. It has to be an energy balance. So if we put these figures in, we can calculate out my primary flow requirement. And my primary flow requirement is going to be my secondary flow, i.e. 72 meters cubed an hour, multiplied by my secondary differential temperature, 15 minus 18, 3, divided by my primary differential temperature, which is going to be 6 degrees supply minus 18 degrees return. And if you were to pop all of that in your calculator and press go, you would get the answer of 18 meters cubed per hour. So the calculated primary flow for sizing this device is 18 meters cubed per hour. And we've also been given the primary pump head and the available pressure, so we can calculate the design authority and minimum authority of these circuits. So let's have a look at sizing again for the three different types of, or in this case, it's three different types of circuit. A standard two-way control circuit, a two-way control circuit with differential pressure control, and a two-way injection circuit with a pressure independent control valve. Again, we want the largest between 0.25 times 60, i.e. pump head, which is 15 kilopascals, and the differential pressure required, i.e. my available head, plus the control valve plus the stud, i.e. 45 minus 3, 42 kilopascals in the case of this, or in the case of here, we have the control valve plus my differential pressure controller is 5, plus the minimum balancing valve is 3, 37. So we're going to be, in this case, sizing for 42 or 37 kilopascals respectively. Again, if we couldn't achieve 15 kilopascals in this circuit, we would need to look at one of these two to preserve a good level of authority. So looking at the valve sizing, for 18 meters cubed an hour, the flow we calculated in the first example. For my standard circuit, we're looking at an ideal KV of 27.75. Again, such a valve doesn't exist without have very deep pockets. So we're going to select the next largest valve with a KVS of 31.5, which comes out at a differential pressure of 32.6. And then my balancing valve has to take out the difference between my available of 45 and my control valve of 32.6. So 12.4 kilopascals, which is a staff 65 at a setting of 4.9 turns. For my differential pressure control circuit, we're now using the figure of 37 kilopascals. Ends up, we're going to select the exact same circuit here, and we also need to select a differential pressure control valve and a balancing valve for 3 kilopascals for the balancing valve, and just calculating what the differential pressure control valve takes out. So in this exact example, we can see the reality is we won't have much improved our differential pressure. Sorry, we won't have much improved our control valve authority, and we'll see in the next slide how, with the addition of a differential pressure controller. So the reality is we'll have bought an additional piece of equipment and not had a big influence on more cost, but actually not really improved it. In the case of my pressure independent control valve, again, it's dead easy. We select a valve for this flow of 18 meters cubed an hour, which in this case is a DN65 modulator. So again, let's look at calculating the authority here. And we calculate the authority for an injection circuit in the same way as we do for a two-way direct circuit. The only difference is how we calculate. The real difference in reality is how we calculate the design flow. So we have my differential pressure on the valve, i.e. 32.6 divided by 60, 0.54. My design authority is the pressure drop across the valve divided by my head, 0.72. In the example of the DPCVs, we do get an increase in authority. Now we're increasing it. It's my pressure drop across the valve divided by my stabilized differential pressure, which in this case is my control valve, my pressure drop on my control valve, plus my differential pressure for my staff, plus my differential pressure variation on my TA pilot, which is it. So it comes out at 0.8. So we do get an improvement on paper, but the reality is the difference between an authority, and we'll see about this in 2 weeks' time, of 0.54 versus 0.8 is honestly relatively minimal. You've already got a really good authority at 0.54. Pushing it up to 0.8, you're probably not going to get really much additional out of your circuit, but you're kind of paying for more to do it. In the case of our modulator, it's exactly the same. My authority is preserved at a minimum of around 0.7. So that's kind of what I wanted to cover today. Looks like we've covered it in about 40 minutes or so. So thank you very much once again. I will leave a final slide as a thank you. If you could take a little scan of that code, it will give you should pop up a questionnaire. If you could fill out a few questions, it's sort of just asking you how the webinar was today. Really helpful for us to have feedback, because we can then use it to improve the further sessions. That is all from the presentation today. What I'm now going to do is I will jump into the Q&A, see if we've got any questions, see if it loads. Let's have a look. I can't see any questions as yet. Double check if there's anything in the chat. Okay, can't see any questions in the chat. What I will do before I go, let me just allow people to turn on their cameras and unmute themselves if they so wish. Oh, I've blocked that, sorry. Turn on their cameras and unmute themselves if they so wish. And just in case anybody's got a burning question that they thought, forgot to write that in the chat, I'll leave it for, let's leave it for a minute or so. Check there's nobody there that's just waiting to ask a question. Okay, fantastic. No questions. Hopefully that means I've covered everything in enough detail to answer all the questions you may have had. If you think of anything in the meantime, please don't hesitate to reach out. I think I've just seen someone's asked, where can we get the previous recordings and slides? If you go onto our website, I will need to find the link. In fact, let me open it up. I will post into here a link to our website, and there is the ANZ section of our website. There is a form you can fill out, and it will give you access to, if you go to, in fact, services, webinars, here we go. I will send, let me go, should be on here. Yes, perfect. I will pop in the chat, I will pop the link to our website, the webinar section on our Australia New Zealand website. If you click on there, you can get access to there's a button to press to say watch the previous webinars. I think you have to fill out a form with your details, and it will send it out. If you've been signed up to this webinar, we will send out a link to all of the previous webinars as well. But that should hopefully be able to be tied up. If you have any problems, please reach out. We're here to answer questions. And I want to say once more, thank you very much, everybody, for joining. I hope you enjoy the rest of your week, and see you hopefully in 2 weeks' time, where we're going to cover control valves and sizing of them in more detail. So we've kind of covered the circuits they live in, and we're going to cover in more detail the bits about authority, why does it matter, different types of thing, how that can affect the overall system, that side of things, in 2 weeks. And then the last session is going to be of this group of 6 will be in March, where we're going to be looking at our software high select, which kind of brings everything together, which brings the balancing and the control in kind of a nice neat little package towards the end. So we're just going to give more, it's more of a demonstration than a training session, I would say, the last one, a demonstration around some of the capabilities of our software that we can use. But once more, thank you very much for joining. Have a great rest of the week, and I will hopefully see you all in 2 weeks' time. Thank you.
Thanks, Rob. Cheers.